I will still have people come in. Hopefully, they can find a seat. But before we start, first, I want to say a big thank you because obviously we are fully seated today for this talk. So I hope this sort of miniature version, 30 minutes subjects could benefit to you all sitting here. So the way I created the slides, because I did this presentation, 3-hour long one recently in Germany, in Stuttgart, and that's the full version. And I will be doing a 1 hour and 30-minute version next month in Oxford. There's a EMC show there. So today, obviously, it's only 30 minutes, but I designed in a way that hopefully benefits you for all. And normally I would ask how many people here are managers, how many people are design engineers, but I guess there's no need to ask. But I have to correct one thing, right? It says troubleshooting EMC like a pro, but actually the correct term should be troubleshooting EMI, because we are troubleshooting a electric magnetic interference as a noise, right? EMC, you don't troubleshoot, but we put this there to attract you here. Lots of people like EMC, isn't it? Okay, so I'll skip this part because probably you know me already. If you don't, speak to me after this session. I do need to mention Telonic, who sort of co-sponsored this speaking opportunity, and we have a stand there. So feel free to visit stands. We have lots of great EMC, EMI, and fast speed measurements set up for today and tomorrow. So yeah, feel free to come over. Okay, so these are the discussion points we're going to cover today. Hopefully, we're going to cover conducted and radiated emissions. I know these are big subjects. Lots of people who are sitting here must have in the past had problems troubleshooting your unit, right? Or had frustration passing EMC. And, the way we look at EMC problems is always like, oh, this is black magic or dark art. And sometimes you really feel like you get a hand of it, right? You say, okay, I master the art of EMC and EMI. And then one time, then you just scratch your heads and thinking, well, what's this then? So it is a very complicated subject. So, cover it in a 30-minute session is going to be challenging. But I'm going to introduce a few useful troubleshooting tools where you can buy at reasonable cost, or if you are really a hardcore pioneer, you can make it yourself, right? And then of course, the performance might not be as good, but you can use it for troubleshooting EMI-related issues. And in the end, I'll provide some references and further reading. So hopefully, if you don't get it today, you can always feel free. Feel free to read the reference. Okay. So as I can see here, we sit here. We have veteran, seasoned, experienced design engineers, I can tell, and we have very many young faces. Well, that's the purpose of this show, isn't it? Hardware pioneers. We need pioneers. So we're going to start with the easy bits, right? Hopefully, this is easy and simple enough for those young engineers. And then we're going to move to a little bit high-level advanced troubleshooting techniques. So both, hopefully, would like this session. Okay, so first is the language we communicate, right? So if you take a product to a EMC test lab, and you often hear the test engineers talk things like, oh, this is a radiated coupling, this is a near-field coupling or conductive coupling. And this is often confusing because what's the difference between all these coupling mechanisms? So this slide shows you the main 4 coupling mechanisms. So here's an example. We have a source and a victim, right? So let's say the source is a personal computer, right? And the victim is a screen. You connect the source and victim both in a power socket here, right? The moment you power these units up, right, in your mind, you should be thinking, wow, there's always a electric magnetic interference as a noise source, right? And the noise can travel using these mains leads, right? Gets into the socket, and behind the socket, you have all the mains, wiring here, right? So that means the noise can propagate through this mains network and affecting the screen, okay? So because there is a hard wiring there, we call this mechanism conducted mechanism. Okay, so that's our first coupling mechanism. Now moving to the next. This one actually is the most important one, right? You really have to understand it so then you can troubleshoot your circuit very, very efficiently. And this is what we call near field coupling. And you can see that we actually have capacitive coupling and inductive coupling. Most of the time, 99% of the time, you will find both coupling mechanisms exist. So you have both capacitive and inductive coupling. So yeah, think about it. What is a capacitor? The simplest capacitor you can make are two conductors, right? Could be plates or wire, and in between you have dielectric. This is by definition a capacitor. So if this is a USB lead, right, whether this end is connected or not doesn't really matter. As long as you plug in the USB lead to the victim, right, and then the source side could have a HDMI cable, right? You all see different types of HDMI cable, different prices. Lots of them causing problems when you plug in because see here, they are very close to each other. And because they are close to each other, you have a strong capacitive coupling, as I said, right? And also, what is a magnetic coupling mechanism? Well, magnetic coupling, we all learn it from high school, right? You have a wire carrying current, whether it is a DC current or a changing current, you will induce a magnetic field. And that magnetic field is what we call self-induced magnetic field. But the moment that you have another wire nearby, then that wire is exposed in this magnetic field. Then they have induced the voltage on this wire. And then if you connect it to a circuit, they will see induced current. And that is magnetic field coupling. So now we have both the capacitive coupling and magnetic field coupling. So now you understand why sometimes when you're dealing with EMC or noise issues, sometimes you just push the cables, for example, close to the chassis, or push the cable to earth or ground, then noise just disappeared. The reason is that you separate these wires, right? And you provide a ground. So that's how you do it, but maybe you don't realize why, right? Okay, so then we have 3 coupling mechanisms already. Now let's have a look at the last one. The last one is what we call radiated coupling. So this is like, what we do here. We do IoT, RF stuff. You have an antenna, right? Put on your phone, you talk, that small antenna can radiate message or energy. You have another antenna-like structure, then yeah, they will pick up energy. And an important thing about this kind of radiated coupling is that antennas are reciprocal, right? So that means if this antenna can radiate noise, then it can also pick up noise. So often you find if a circuit or equipment is very noisy, you can also have problems, in terms of immunity issue. So here we go. We have the 4 coupling mechanisms introduced to you. Now let's have a look at some real-life examples. So in the first video I'm going to play, it shows you the conducting emission measuring using a differential probe, right? Very simple, just measure the voltage and I measure the current. And the current measurement I do is using what we call an RF monitor probe. So this is really just monitor the noise in my household, right? And I show you different noise. So especially for young engineers, you can really appreciate the noise. So this is really just coming from the lights. And you can also see that this voltage waveform actually in your household is never really a pure sinusoidal waveform. You have like flat on top. That means lots of harmonics in your house, right? This is a blender. The moment I press it, you see that noise is generated by the motor drive, and there are lots of noise there. Okay, so that's a blender noise. Yeah, see that? This is a zoomed in version, right? And what is next? Next is the microwave oven. So I put it as a microwave mode. So you can see that these are conducted emission generated by the microwave oven, right? So these are the noise we measure on the mains network. So, you can imagine why there's a need of complying with, all the EMC standards because they can interfere with each other. This is interesting. This is a kettle. The moment I press, right, switching on and off, you get this transient noise. See, that's the transient noise we talked about. Now you understand, oh, why? When I send a product for EMC testing, I need to pass conducting emission, radiating emission, and also transient tests because, a small kettle like this, you just switch on and off, generate a pulse like this. And if you're really good, like you're an experienced engineer, you look at the shape of this pulse and you probably recognize this is exactly, or not exactly, but very similar to the pulse that you see on a generator called electric fast transient generator or burst generator. So you see the tests are actually designed because of what we experience in real life, isn't it? Okay. So the next, I'm going to show you magnetic field coupling. So in this case, you can see I have two loops. When the loops are close, you see strong pickup from the victim to the source. But here I have a copper shield, you see, and I can just block the noise. But the moment these two loops are moving close to the edge, you see more noise is being picked up by the pickup loop. So this shows you the magnetic field coupling and how we can reduce it, right? Think about your application. If you're doing with cabinet design, things like that, this is actually your cable tray. Your cable tray actually provides functions like this, right? So this is magnetic field coupling. Now the next is, some people would say, oh, the next, I think it could be radiated coupling rather than E field coupling. So what's the difference? Because you think about it, I mentioned there's a near field coupling and there's a far field coupling. What's the boundary? Well, that's something more advanced, not within the scope of today. But this is another type of coupling, but this is an immunity issue. This is a vehicle I worked with, right, in the past. And this is a door. And, we can trigger the door open and close simply by using this walkie-talkie. See? The walkie-talkie, just press the walkie-talkie, and then the door is open and closed. This is what happened here is, this can be seen as a noise source, okay? It generates a fixed frequency pulse. Through this antenna, or you can treat it as like a conductor, this then near field coupled to the wiring behind this door, right? The wire has a button that has electric circuit on it, and somehow that noise signal travel all the way back to the vehicle control unit, and the vehicle control unit got confused, saying, oh, somebody is pressing the button, but actually no one is pressing the button. So you can see that there's a need for dealing with noise issue in real life, okay? Right, so as I mentioned, to measure noise, now we have, now you understand all these sort of coupling mechanism, and we look at the types of noise. With this kind of noise, where you see like the microwave oven is switched on, right? This is what we call continuous noise, because this noise, when the unit is switched on, the noise is always there. So in order to capture this noise sort of in a very accurate manner, we use what we call spectral analyzer or receiver, right? So this device works in a way that has a window that just sweeps across the frequency range you define, and it will stay there and then measure the noise level and then record it. Simple like that, right? But the problem is this swept type spectral analyzer, as you can see that. For example, if I'm the sort of the window I talked about, right? So I sweep from, let's say, 10 kilohertz, and I want to measure noise up to 300 megahertz. So I do like this, moving at a speed, right? But the problem is, if I start from 10 kilohertz and I'm moving in this speed, then all of a sudden there's a noise, for example, 300 megahertz, and I miss it. So for that kind of transient event, this would fail to capture the noise. Therefore, for transient events, like the kettle, for example, we use oscilloscope, because the oscilloscope can capture that fast sort of event. But of course, then you need to check the bandwidth of oscilloscope, right? Because if it's an ESD, right, we all experienced ESD event. For ESD event, I would highly recommend a gigahertz bandwidth scope to capture the shape and the sort of the pulse level. Okay, now this is interesting actually. This slide I added because through my training, I do training pretty much every 2 weeks or so, to different companies, big to small. And I realized that, lots of the young engineers, we graduate from the university and we forget about the basics, right? So I asked the engineers, I said, look, you use the scope. Yeah, we use scope. Passive probe, yeah, 10 to 1, correct. How does it work? And you only got like 2 or 3 people can answer the question. But it's so simple. When you have a passive probe connected to a oscilloscope, right? You measure a signal. Let's say here we have 5 volts. How does it work? Well, basically, in the probe you're using, they have a 9 mega ohm resistor and a 1 mega ohm resistor. So you have a sort of potential divider, right? So then Ohm's law, simple. So if it's 5 volts here, I get 0.5 volts here. And then because it is a 10 to 1 probe, what the oscilloscope does is just multiply by 10, then you have 5 volts. Simple, right? Simple. But think about the situation where I show here, right? This is how you normally measure a signal. So the probe tip measure the 5 volts, as we mentioned, has to be grounded, of course. Then this is the ground lead. So you look at it for lots of the young engineers, you'll be thinking, wow, this is looking good, right? I've seen signals, I've seen noise. But the question I'm going to ask you is, are you 100% confident that the noise you're measuring actually comes from the measuring point you measure, right? Because you think about this, look, this is what we call a loop antenna. I tell you what, if I short this ground pin to the tip and I just put this here without touching the circuit, I possibly measure some noise, right? So then, the signal you are measuring perhaps is not really the true signal, right? So another issue with the passive probe, right, is that you have the so-called parasitic capacitance. Parasitic capacitance is inevitable, right? As we said, as long as you have metal and in between you have dielectric, you have capacitance. That is why, right, if you buy a whole new oscilloscope, read the manual, right? The first step they ask you to do is connect the probe to a signal source they provide, right? And you see this square wave. And then they give you this little tool so you can sort of tuning or calibrate the probe tip. Therefore, the voltage waveform you measure is a true square wave. And you may wonder, why do I need to do that? Because what you effectively do is tuning this capacitance it provides. Therefore, for high frequency, you are also measuring the true signal. I mean, for DC, you don't really need to worry about these capacitors because we all know that at DC, the capacitance is a short or open circuit, right? But at high frequency, this becomes low impedance, this becomes low impedance. Now, you look at this resistor, you think, I have a high impedance resistor, 9 mega ohm, 1 mega ohm. But in fact, if you're measuring a noise signal at 100 megahertz, which is very common, right? Common 100, 300 megahertz, you are actually loading the circuit. When I say loading the circuit, the noise would travel, for example, from here through this capacitor to us. And to make it worse, this capacitor would also load the circuit you're trying to measure. So sometimes you see a problem, and the moment you're probing the circuit, the problem disappeared. And you sort of, magically, I fixed the problem simply by probing it. What is really happening is you load the circuit, okay? So that's the problem with using the so-called high impedance probe for EMC or noise troubleshooting, okay? So that's the issue we face. So how do we deal with this issue? The issue, as you can see, right, we've talked about the capacitive loading and the inductance effects of the long grounding leads. You can, of course, shorten the ground lead. Lots of people sitting here know that. But how can you avoid the sort of the loading? Because you need to probe that pin, isn't it? So here, that's the reason we introduce these non-contact tools. So the most sort of useful tools in my personal experience, of troubleshooting EMI issue for more than 10 years, is this near field probe and RF current probe, okay? So we're going to look at how they work. But if you look at this, first thing you notice that actually, this is actually non-contact because this is a donut shape, right? So you put the wires you're trying to measure the noise on the cable, for example, you just clamped it and you don't actually contact the circuit. And same with this near field probe. When you are sniffing on a PCB, you see you are using the near field coupling, right? We introduce the near field coupling. You are using the near field coupling, so you don't actually sort of load the circuit by making that contact. So that's how we prefer these two tools for EMI troubleshooting. So first, let's have a look at the magnetic field loops. The way it works, right? Simple. You got a noise source here, and remember we mentioned magnetic field coupling, right? So you've got noise current going this circuit, generates field, the other conductor here, because it's exposed to the same sort of field, right? It sees voltage across it, right? And the beauty of this kind of probe is that if you look at these two, for example, these two conductors, because they are perpendicular to this conductor you're trying to troubleshoot. This could be a wire or it could be a trace or track on a PCB. But this, because it's 90-degree perpendicular, these two actually, if you look at the math or physics, they don't have induced voltage. And this conductor here is so far away from the circuit you're trying to diagnose. Therefore, you only measure the noise using this conductor. And that's how simple it is. That's how it works. And lots of people buy these sets and without really understanding how these things work. And that's it, right? And yeah, then we measure the noise. But here's the tricky thing is, when you are connected to a spectral analyzer, then by default, this output is connected to a 50 ohm impedance, okay, 50 ohm load. Whereas if you are choosing to connect this to a oscilloscope, then this has to be terminated with a 50 ohm impedance. Okay, that's important because these things are RF circuits. You've got a 50 ohm coaxial cable, so you terminate with a 50 ohm impedance to avoid reflections. Okay, so I'm just gonna skip this. Yeah. So speaking of near field coupling, here gives you a few examples of this mutual inductance thing, right? So two adjacent wires, like this could be your power, so 12 volts and 0, or live and neutral. These two are together, and typically speaking, the sort of coupling factor is about 0.5. You can improve that, right, by using twisted pair or keep these two wires close. The best is to use coaxial cable. That's why lots of the application RF, we always use coaxial cable because these are K almost equals to 1. That means mutual coupling is very, very strong between the center conductor and the shield. So often gives you very good signal integrity, power integrity, and EMC performance. Okay, so we have 10 minutes left. Let's see if we can cover some more advanced techniques I use. So these are very practical. Of course, I can't show you the PCB I'm working on, but I just show you the techniques I use. So for example, here you can see 4 traces, and you can see here my near field probe was probing something, okay? And here you can see the results. And the thing is, if I look at the green trace, look at the shape of it, compared with my tensile measurement. Tensile measurement is another device I can show you later downstairs. But if you look at the profile, they're very similar. So you're almost certain that, okay, if we fail the radiated emission in this frequency range, it's gonna be this circuit here I'm probing, okay? So that's how you're using a near field probe connected to a spectral analyzer, find the noise source. Okay, this is really advanced stuff, and I just wrote an article on this, and this is quite amazing, right? To keep long story short, right? This circuit, when the client contacted me, he said, look, we failed 600 megahertz. And I said, 600 megahertz radiated emission, I can fix that. And I just by default, I said, 600 megahertz narrow band failure. So when I say narrow band failure, is you look at the frequency plot, it's just one spike, pretty much like this. This is what we call narrow band. But then they show me the result. They said, look, like this. And I said, wow, this is a broadband failure. So this is what we call broadband because it's quite broad, right? And I said, look, I never seen this in a 600 megahertz range. Normally it's like 200 or 100 megahertz range where we have lots of problems with the radiating emission. This is weird. And it took me a long time to find the noise source. But the point I wanted to make for today is that, okay, finally we found the problem. It's a Schottky diode, okay, used for a buck converter. But how do I prove it? When I give a client a test report and my sort of troubleshooting report, I need to be 100% certain what I'm talking about, right? So I need to prove it. I can say, okay, I remove the Schottky, right, and I measure it again, the noise is down. Of course, that's one way of proving it. But a better way of proving it is to show them some measurement results. So here it shows you the difference between the two. In the first case, you see, I'm just using a probe, and I shorten the ground lead to the this is the ground lead, very, very small, right? And I measure the voltage across this Schottky diode. And in the next case, I'm using this small near field probe, okay? You can see that, right? And I compare these two waveforms, and you can see, right? So if we look at this picture, first we see that every time when the Schottky is switching on and off, you see a big spikes here, okay? So that indicates there's a noise issue there. And then if you zoom in, okay, then you can see the spike is actually overshoot and ringing, right? You got overshoot, undershoot, and ringing. Now, if you look at this is the frequency range, yeah? This is what they measure using the antenna. And it fails about 600 megahertz. And if you compare the time domain measurement and you just measure between the two peaks, that will give you the times, right? And then you do the 1 over delta t, that gives you the frequency. So when I say 625 megahertz, I can confidently tell them it is due to this Schottky. But remember I said this measurement could potentially load your circuit because you are making a contact. And let's see if that's the case. It is the case because if you look at the blue trace here, I mean, if you measure the peak here and the peak here, you may just be able to measure that 625 megahertz, but it's not obvious. However, if I use the non-contact measurement, say here, in the true real-time sort of oscilloscope capture, you can see the overshoot and ringing, and you can easily measure these peak and nulls. Whereas this one is a little bit loaded. Okay, it's not a big deal, but still you can see the benefits of using non-contact measurement. Okay, so same probe. Remember, EMC is all reciprocal. So if you can use the near field probe to pick up noise, you can also use it to inject noise. So this is a video I show you where I connect this to an RF amplifier and using the spectrum analyzer tracking generator, generate a noise, and I just sniff again on this PCB. And at one point, you can see the LED lights got disturbed. So let's have a look. See that? So in this case, you see it's the noise generated and affecting the PCB. Again, the coupling mechanism is near field coupling, right? Near field coupling. So when you send the product in an EMC test lab, you fail in the far field. How do you troubleshoot? You go to the near field to troubleshoot, right? That's how you do it. You cannot really troubleshoot from the far field, okay? So yeah, this is the current probe. So we introduced the near field probe. This is the current probe. And I just look at the time. We have 5 minutes left, so probably not enough to cover how these things works. But you can see the construction of it. So you can see the challenge the manufacturer makes these. And in terms of how they work, very simple to the near field probe. Magnetic field coupling is just that now you have a core, magnetic core. So the mutual coupling is a lot stronger. So you can pick up very, very sensitive noise. Because I think lots of, we're sitting here, you're doing avionics, aerospace, automotive, defense. These are, the noise level by standard is very, very low. So you have to use a very sensitive probe in this case. So here shows you an example again. Lots of people will tell you, especially if you speak to a lab manager, right? They will say, look, you cannot test EMC. You have to come to our labs, which is true, by certain extent. But just to show you, I went to a company, a client, right, years ago. I just use this current probe, right? You see the way I clamp it. I clamp on these two big shielded cable, right? And these are DC-DC converter, 200 amps, by the way, on the output. I just managed to push these two wires as a common mode measurement on this current probe. And I measure it using my spectrum analyzer. And by doing some clever algorithm I developed myself, I can match what they got from the EMC test labs, okay? So that actually gives you benefit because you send the products for EMC test cost you about £2,000 or something a day, whereas you can actually implement these schemes and then you can do it in your office, okay? So you can see the results are pretty, you can't get 100%, right? You can see here, especially here, it's not really matching, but it doesn't matter if you're trying to troubleshoot in this frequency range. If you bring down 10 dB, job, you got confidence that you will pass, for example. This is another client's product where, their ambient noise is very, very noisy. I cannot use my antenna when I travel to their office. So I use the current probe, the one I just showed you, clamped on this side, clamped on this side. This is a motor drive application. And the beauty is, again, you can see that as long as you can see the noise profile, you can troubleshoot because they are the same as what you get from the lab. So these are the lab results. These are what I got from my visit. So if I can see this, I can solve this, right? Because sometimes you can't see it. That's the problem. Okay, so this is the techniques you often use to separate differential mode and common mode noise. Well, if you want to know the details, we can have a discussion later on. But lots of the problems we're facing in our challenges are radiated emission or conducted emission in high frequency range, so sort of 20 megahertz all the way to 200 megahertz. Then you are dealing pretty much with the common mode noise. So this is how you use the probe to measure common mode noise. If you want to measure differential mode noise, you're going to be very careful because the core could easily get saturated. So if you have like a few amps going through this sort of power and ground wire, I wouldn't use it because these things, when it gets saturated, you don't have accurate results. Okay, and 2 slides more. So basically, same technique can be used for troubleshooting transient. So this is the case where I use the near field probe or the current probe connected to a oscilloscope and during the transient, I look at all these locations, right? Putting here, putting here, putting here. And what you find is if a system failed during the transient test, often it's nothing to do with the peak, okay? That gives you some energy, but often it doesn't fail the system. What it failed the system is often the the swing, so the overshoot, undershoot, and the ringing. So if I find, for example, in this case, the blue trace, look at the ringing. I would definitely, let's say the blue trace is what I measured from here. I would put a ferrite core here to dampen that ringing and then fix the problem. So this ringing is often the problems. So if you see a ringing in your system, fix it, okay? And finally, the last slide is you can also, if you have the opportunity or fortune to have a ESD gun, you can use the ESD gun not only for ESD testing, you can use it for many things, troubleshooting immunity, right? For example, in this case, I put a foil around the cable and I zap the foil, and then the noise can also be seen on the cable. And you know what? This is capacitive coupling. Think about it. Between the foil, between the wire, you got insulation. That is capacitive coupling. And in this case, I do it in a way that is magnetic field coupling because I wire that earth wire of the ESD gun and I generate the noise. So yeah, you can use the near field coupling mechanism we introduced. And then look, these are the waveform we measured using the current probe. Okay, so the last one really quickly is that, again, you can use both near field probe and RF current probe connected to a oscilloscope, because if you're using spectral analyzer, you only have one input. But with an oscilloscope, you have 4 inputs, and then you can use it to trace where the problem is. So you connect the probe on the cable. That gives you the common mode noise. Often you fail in the lab. And then the other channel, you connect it to a near field probe, and then you sniff. So in this case, this project is in Cambridge, and use this, and you can see that when I see 2 waveforms, in sync, that's how I know where the noise is. Okay, finally, there's a big conference on EMC signal and power integrity in Oxford. It's scheduled for May. I would highly recommend the seminar and the workshop. It's not going to be me presenting, but with experts from the United States, Austria, Germany. They all come and present. So speak to me after this. I can give you a discount code. It's in Oxford. It's in May. So definitely highly recommend. Okay. Thank you very much for showing up today. Thanks.